Let's finish class today by studying example 3. Consider the extension Q adjoin 4th root of 2 adjoin I of not Q, but Q of I. Q adjoin I. This is a little different. The base field is not Q. It's Q adjoin I. You can think of Q of I, since I is a root of x squared plus 1, degree 2, irreducible over Q, x squared plus 1, can be written as a linear combination of 1 and I with coefficients from the rationals. 1 and I form a basis with 2 elements for Q of I as a vector space over the rationals. It's got dimension 2. And therefore the degree of Q of I over Q is 2. Q adjoin 4th root of 2 adjoin I is of yet a bigger field, because now we're adding in 4th root of 2, as well as other things. By the theory back in chapter 19, the new chapter 19. Well, you could think of this as take Q of I and adjoin 4th root of 2. And it does turn out to be a degree 4 extension of Q of I. It turns out, without proof, that x to the 4th minus 2, thought of as a polynomial in Qix, is in fact irreducible over Qi. That's not obvious. You can't apply Eisenstein's criterion to that, because Eisenstein's criterion only applies when your polynomial actually has integer coefficients and you're thinking about whether it's reducible or irreducible over Q. This does have integer coefficients, but we're not thinking about whether it's irreducible or reducible over Q. What this ultimately means is you can write elements of this as linear combinations of powers of 2 to the 1/4 power, where the coefficients are in Q of I. I could write A times 1 plus B times 4th root of 2 plus C times 4th root of 2 squared, which, by the way, is square root of 2, plus D times 4th root of 2 cubed, where the A, B, C, and D are not rational numbers, but they're in Q adjoin I. They are of this form. And that would ultimately mean, though I'm not going to write it all out, that this field is a degree 8 extension of Q, with the basis having 8 elements, 4 of which are these numbers, and the other 4 of which are when you multiply those numbers by I. In fact, this is all related to this diagram here. There's your base field Q. Here's the field we're ultimately talking about, the biggest field extension in example 3. In this picture, Q of I is right there. But there's plenty of other intermediate fields between the base field Q and the bigger field Q adjoin 4th root of 2 comma I. And ultimately, if you multiply the numbers along these lines from the smallest field to the biggest one, no matter which way you go, you get 2 times 2 times 2, 8 is the degree of this extension over the rationals, it turns out. And the Galois group, it does turn out to be a situation where the fundamental theorem of Galois theory applies. The Galois group of this thing over Q turns out to have 8 elements. Up there, here's the subgroup lattice for the Galois group. It's got 8 elements. Example 3 is just working our way towards there. we're almost out of time. I would strongly encourage you to continue studying this. Do notice we're continuing to use this trick of writing 2, for example, as 2 is phi of 2, right, as 2, the 4th root of 2 now to the 4th power. Ultimately, phi of the 4th root of 2 does still have to be a 4th root of 2, which does include 2 real numbers, but it also includes 2 complex non-real numbers, though they are simple multiples of I. In the complex plane, the numbers are going to be either on the real axis or the imaginary axis, and that does simplify things a bit.